So good morning, good afternoon, and good evening. Welcome to the MOF 2024 series webinar. Today we'll have the 8th webinar and also the last webinar of this MOF 2024 series. Before today's webinar, please allow me to introduce MOF 2024 conference, the 9th International Conference on Metal Organic Frameworks and Open Framework Compounds, to be held on July the 15th to 19th, 2024 in Singapore. The International MOF Conference focuses on recent advancements in metal organic frameworks, MOFs, covalent organic frameworks, COFs, and other porous materials. And this series of international conference is the most well-established conference in the field with close to 2 decades of history. As you can see from here, the International MOF Conference started in 2008 in Germany, and then in 2010 in Marseille, France, 2012, Edinburgh, UK, 2014, Kobe, Japan. That was the first time in Asia. And then 2016, Long Beach, USA, 2018, Auckland, New Zealand, 2020, due to the COVID, it was held online. The last one, 2022, was held in Dresden, Germany. And this time, it will be held in Singapore. So Singapore is a country in Southeast Asia. It's close to the equator, and is a land full of opportunity and mixed culture, mixed food, all kind of beautiful gardens, beautiful islands. I'm very sure that you will enjoy your stay in Singapore. So the MOF 2024 conference is held by Materials Research Society of Singapore and co-hosted by National University of Singapore, the Nanyang Technological University of Singapore, the Singapore University of Technology and Design, and the Agency of Science, Technology, and Research. So we have 5 main themes and topics. They are materials, fundamental phenomena and properties, synthetic methods, characterizations, and applications of industrial integration. So we have a 2-day pre-conference to be held on July 13th and 14th. And after that, we have a 5-day main conference starting from July the 15th. It will end on July the 19th. The 2-day pre-conference will be held at National University of Singapore, U-Town. So if you have not been to NUS before, please come and visit us. I'm sure you will enjoy the campus visit. So this is the schedule for the 2-day pre-conference. On the first day of the pre-conference, we'll have a Young Investigators Symposium, where we'll invite some young investigators come and share with us their research, and we start to build network. So the pre-conference will start at 8 o'clock for the registration. After the brief opening, we have the plenary presentation by Professor Suzumu Kitagawa from Kyoto University. And after a refreshment break, we'll have 8 invited presentations. And in between, we'll have lunch, and we will provide refreshment break and poster visit as well. So on the second day of the pre-conference, we will organize the materials characterization workshop, and we will introduce some technologies that are very important for the modern study of MOFs and COFs, especially those materials with small crystal sizes or poor crystallinity. For example, we will introduce the 3-dimensional electron diffraction workshop. We have 2 lectures on that. And we will introduce the applications of X-ray total scattering method, and then X-ray absorption fine structure spectroscopy. And those will be very useful for some materials with low crystallinity and even amorphous material structures. And last but not least, we will have another lecture on the advanced absorption characterization of MOFs for CO2 and VOC capture. And after this, we will organize a social visit. If you have registered, you get a chance to visit the Garden by the Bay, where you will refresh and prepare yourself for the main conference. The main conference will be held in next Monday, starting from 15th to 19th at Suntec Singapore Conventional and Exhibition Center, which is one of the largest conference center. And on Monday, the first day of the main conference, in the morning, we will have another social visit where we specifically arrange this one for those of you who visit Singapore for the first time. So during this half-day social visit, you will have the chance to take on a bus, and we will drive you around so that you will have a view of the city. The conference registration will start in afternoon, starting from 2:30 until 5 p.m. And we will start our opening ceremony at 5 p.m. And then we'll have our first plenary presentation for the main conference, and then followed by the reception. On Tuesday, we will continue the main conference. After introducing the exhibitions and sponsors, we'll have a plenary presentation, and then we will split the whole conference into 5 parallel sessions. And each session will start with a keynote and invited and oral presentations. And on Tuesday and Wednesday, we'll have poster parties. And specifically on Wednesday afternoon, we'll have the editors forum. I will introduce that later. Thursday, the same, but we'll have the industry forum in the afternoon. At the end of Thursday, we'll have the gala dinner, where Professor Omoyagi from UC Berkeley will deliver a plenary presentation in the gala dinner. On the last day of the MOF 2024 conference, after the plenary presentation, we have the 5 parallel sessions, and then the 6th plenary talk, and then we will give out the best poster and best paper awards. We will close the conference, and we will have another social visit as well. So that's the whole plan for the MOF 2024 conference. So this gives you an idea about the size of the conference. We have 2 special speakers, Professor Kitagawa and Professor Yagi. And we target at close to 1,000 participants, including 8 plenary presentations, 47 keynote presentations, 79 invited presentations, and in total, 163 oral presentations with 680 more posters. So we have pre-conference, we have editors and industrial forums, gala dinner, and the social visit. All these activities will make MOF 2024 a very rich conference. This is the editors forum. We have invited editors from the flagship journals in chemistry, material science, and the chemical engineers. So that will give you a good opportunity to interact with those editors and get some ideas how to publish your best work in those papers, journals. And then we have the industrial forum. We have invited speakers in the whole MOF industry chain, from the MOF suppliers to the MOF users, and also some of the investors and technology providers. We believe that by bringing people together, we'll come up with new ideas that can keep advancing this whole area. This is some statistical data for the abstract submission. By April the 8th, we have received more than 1,000 abstracts. Close to a quarter comes from China, but we also have substantial numbers of abstract submission from other areas of the world, like Germany, United States, United Kingdom, etc. And these are the distributions of the submitted abstracts in the 5 themes. The majority are in the materials and also the applications and the industrial integration. Here is the registration statistics. As of May the 27th, we have received 777 registrations. And almost all the social activities have been registered, reflecting a strong interest to the activities that we have organized. So if you're interested in MOF 2024, you can still register for it. This is a conference website, and we have our social media platform. If you're interested, please follow us. And we look forward to welcoming you to Singapore this summer. So thank you for your interest in MOF 2024. And now let me introduce our speaker for today's webinar, Professor Jingwei Hou. So Associate Professor Jingwei Hou is a chemical engineer working at the University of Queensland. He received his PhD in chemical engineering at the University of New South Wales in 2015. Then he conducted his postdoc research at the UNESCO Center for Membrane Science and Technology and the University of Cambridge. He joined the University of Queensland in April 2019 as an ARC DECRA Fellow and is a recipient of the ARC Future Fellow in 2021. And those are highly competitive. And Dr. Hou's main research area is in the microporous materials and their applications in separation, optics, biocatalysis, and energy applications. He has 1 book chapter, 2 patents, and over 150 research papers published in Science, Nature Com, JACS, Chemical Society Review, Anglevanti, CAM, Advanced Material, etc. So he has received over 10,000 citations with an HDEX of 59. Aside from his primary research, he enjoys hiking, videograph, jogging, and playing the piano. So without further ado, Jingwei, the floor is yours.
Thank you, Professor Zhao, for the kind introduction. I will try to share my screen, and I just want to make sure everybody is seeing my screen. All right.
Sorry, Professor Jingwei,
yeah.
we see the
Yes.
moderator view. If you can swap, please.
Oh, can we swap? How about now?
Perfect. Thank you so much.
Brilliant. Thank you. First of all, I'd like to thank the organizing committee for inviting me for the webinar. I think in the past years, we've been getting used to webinar quite a lot. But still, I want to say thank you so much. And it's really good opportunity for me to get this pre-engagement before the exciting conference Professor Zhao just mentioned. So I think today I'll be taking the opportunity to talk about some of my research. It's mostly about the nanocomposite metal organic framework materials. As Professor Zhao just mentioned, we've been looking at different variety of different applications, including membrane science, material engineering, energy optical applications. But it will be fun. My talk is mostly regarding how we came up with the idea rather than just the pure scientific stuff. So hopefully that'll be something useful and inspiring. This is the kind of roadmap of my research. Been working on different topics like the gas, water, energy, data science, and bioscience. But all of them are centered around this cluster we call it metal porous materials, which I believe all of us should be very familiar with. But before I jump into the topic, I always like to start my talk with this question. So if you're the first time come to my talk, probably you can start thinking about the answer to this question. This is a question kind of bothered me and keep me thinking for over 10 years time before I really come into the, I would say, ultimate answer to this question. So the question itself is, what is the most compatible material or matrix that work with MOF? MOF is a pretty good material, but how can we make it even better? So I'd like to start with my journey, how I found the answer to this question. As Professor Zhao mentioned, I was a chemical engineer. I was a very hardcore chemical engineer. So if you look at my track record, publication record, particularly at the beginning of my career, it is really, really bad. I mean, I can gather around 3 or 4 citations each year. That is pretty much nothing from today's standard. So that is kind of because, of course, back then people published much less. And also I spent quite a long time working in pilot scale projects when I was in my PhD, as well as in the first postdoc when I work as a research fellow at the UNESCO Center for Membrane Science and Technology. So this is what we did. Basically, we developed this whole membrane rig and took the membrane rig to a power station in Australia, which is about 200 kilometers away from Sydney. So I drove to the power station on a daily basis, collect the samples, do the membrane testing, go back to the lab to do the sample analysis. It is a pretty exciting project. We basically build the whole rig and bring it to the power station and test the membrane. So it's very long project, and I found it's pretty interesting. So at the beginning, what we're trying to do is we use polymeric materials, as everybody would expect it. It's quite cheap, it's quite easy to make, and also it's quite scalable. We have set up a membrane spinner inside the lab, and we can manage to make large batch of membranes and test those membranes under real flue gas conditions. That's quite interesting because I like the big stuff. I like the big equipment, I like big instruments, but the membrane does not really like the flue gas as I did. You can see we even though we have optimized the parameter of the membrane in the lab, but the membrane will not last long in real flue gas conditions. So we test the membrane for a really long time. So for example, looking at here, we're over 500 hours. I mean, the initial 300, 350 hours looking pretty okay. It's not spectacular in terms of the performance, but it's pretty consistent. But after a certain point of time, you see the huge, very clear, evident drop of the membrane performance. Let me see what I can bring out later. Yeah, which is not ideal. So we took the membrane back to the lab and we get the membrane module. If you look at the membrane module, you can probably guess where the problem is. The flue gas contains a lot of very acidic, very corrosive chemicals. When it gets in contact with water, it will form acid. They are so not rusty. Even the copper tube could not sustain, not to mention the polymeric membranes. So this brings me to the first question. So how we can solve the problem? I mean, this project was done around 10 years ago. That's quite a long time ago. At that time, and even today, people are still looking at the primary and number one solution to this advanced membrane technology is mixed matrix membranes. And we shorted for M or MMM. So I always like to see things from the opposite way. So what would give us if we see it opposite for the MMM? So we turn it upside down, it becomes a 3W. So actually the MMM, the M actually looking from my perspective, is actually 3 questions. So what material we should choose to make the membrane, and where should we put the materials, and when should we incorporate those materials into the membrane, either pre-synthesis, either in situ formation, or even post-treatment. So if we can, I believe, if we can answer those 3 questions, we can solve the M question pretty well. So of course, we have done some literature review, and also we studied how we can make the membrane better. Of course, one of the ideas is to incorporate some advanced materials into the polymeric substrate, which is quite straightforward. This is what people do in a lot of like traditional composite membranes, in a lot of like traditional advanced materials. But which material or what material should we use? Like just I proposed in my last slide. This introduced me to the MOF world, also the topic of the conference. I'm pretty sure I don't need to go through another introduction for the MOF itself. To me, I think MOF is just like a Lego. We can design different pores, we can design different structures, which is perfect for chemical engineers. We can achieve theoretically, we can achieve precise molecular saving by using the MOF structures. But as I mentioned, I was a chemical engineer. I know very little about synthetic chemistry. At that time, I even don't know how XRD works. So basically, the first thing we want to do is whether we can try something that's well studied and something has been, people have been understand the properties of the material very well, so we can get it off the shelf and put it into the membrane and see what happens. So we started the whole MOF journey by choosing two types of materials. One is ZIP8, the other one is UIL66. So again, I will not go to the details. Everybody should know those two materials very well. So something pretty exciting happened after we put ZIP8 into the polymer. You see, if we look at the top two lines, this is what happens for the pure polymer membranes. How membrane can achieve gas separation or water evaporation is because between the polymer chains, there are some free volume. The free volume allows the molecules that we want to separate either go faster or even just go slower through the membrane. But if we expose the membrane, which we have to keep in mind that it's ultra thin, it's not super sturdy. If we expose the membrane against the high pressure, as we did in the flue gas environment, those free volume will be gradually compacted. In this situation, we will lose the membrane performance. We will lose the permeance, and also the membrane is not going to be very selective. So what happens is if we incorporate a very benchmark MOF ZIP8 into the polymer, because there are so many chemistries in the MOF as well as the polymer, so they can form a lot of chemical bondings like that. Not chemical bonding, hydrogen bondings between the crystal and the polymer. So that actually gives additional mechanical strength at the molecular level for the composite. That's making the membrane much more robust and much more durable, particularly against high pressure. So in this paper, we actually test the membrane in lab against up to 35 bars. And for the composite membrane, it still survives and can keep the original permeance after pressurization, depressurization cycles, which was really, really exciting. But once you have two materials, you solve one problem, and you're actually creating a lot of more problems. So this is particularly more important for non-composite membranes because we're talking about the ultra-thin layer. We're talking about putting two materials that probably don't like each other together. So what happens if we have something not really compatible is we're going to create some voids at the interface. So if we use the membrane for gas separation or for water treatment, what will happen is the gas vapor will bypass the super advanced fillers that we really wanted to go through. It's actually bypass the advanced filler, go through the voids across the membrane, making the membrane actually less selective. So this seems like a not so difficult question to solve, but if we want to make it compatible, we need to think about another thing. What happens if we make it too compatible? We can actually functionalize the MOF. We can actually use the MOF polymer. Say we put organic polymer chains on top of the MOF, which can say even participate the polymerization of the polymer membrane itself. But in this case, we're actually creating a more rigid, more robust interface between two materials that can actually slow down the mass diffusion within the membrane. So this seems like a very fine balance between two sides of the huge issue. So how can we solve that? Again, we're very lucky to work with a bunch of chemical scientists, particularly with Professor Diana Andreso from Sydney University and also Dr. Weibing Liang. They've been very kindly helping us to synthesize the functionalized UIL66 by using different kind of ligand. And then we managed to put the functionalized material into the ultra-thin polymer separation membranes to see the membrane performance. What really surprised us is we can actually put up to 80% of the functionalized, in this case, amine functionalized UIL66 into the polymer. And we are not really losing the selectivity for the CO2 and CO2 and nitrogen selectivity. So that's really, really exciting. So we published a paper And we highlight this one, highlight the concept. This is pretty much like design the material based on our needs. So that's pretty exciting. So after working on the triple M mixed matrix membrane for a couple of years, I start to think, okay, if we believe the MOF material is such a good candidate for membrane, so why wouldn't we just make a membrane out of the pure MOF, or at least using the pure MOF as a selective layer to make membrane? So wouldn't that be a fantastic idea? Of course, it may sound pretty good, but in practice, it's really, really hard. I mean, you have to first of all, we need to think about the mechanical property of the MOF, which is another huge topic. I would say the mechanical property of the MOF is good, but it's not superb. So making a thin film out of the MOF powder, it is really hard. And then again, this has to be pinhole and what we used to call it defect-free. But actually, there's nothing really defect-free. So how we can control the defects within the thin film? We're talking about hundreds of nanometers thin, or even thinner. That's pretty hard. So if we want to roll a MOF on top of polymeric substrate, this is what we usually end up with. Typically, we want to start something commercially available. Say we start with a PVDF membrane, which has been widely used for water treatment and all the applications. But anything has been widely used in industry. That means typically those materials are not really reactive. They're quite inert. They're quite robust. That means they don't really like MOF to be grown. So this is what we can get after we soak the polymer PVDF membrane into the MOF precursor solution. We try to grow MOF on the top, but we don't get nowhere near the coherent continuous layer. We will never use the membrane for gas separation because it will never achieve any separation efficiency. So how we can solve that? One thing is we want to make the polymer and the MOF material liking each other more by introducing some intermediate layer in between. So we have a polymer material. In order to do that, we can do it either by physical treatment, that means increasing the surface area, and also we can introducing some chemical bond that can increase their affinity. So we actually, we thought, okay, why wouldn't we do it both? So this is how I did it. We start with a pure polymer material, and we use a sol-gel coating technology to coat the TiO2 nanoparticles on the surface. This is what we get. We can actually control the particle size, we can control the morphology, and also don't forget TiO2 surface have a lot of functional group which can be further treated to introduce organic silane, which will be later used for CO2, which can be later used for Z-plate growth to in situ nucleate zip crystals on top of the surface. It is not an easy process, but we were really happy to end up having a kind of coherent, continuous thin film coating on hollow fiber tube membrane surface. This is pretty hard. And of course, once we have the film, we were really excited. We want to test the membrane performance. Again, this is a super busy table. I don't want to read out all the data, which I'm pretty sure will put everybody asleep. But what I want to highlight is after a certain period of time of the crystal growth, we can achieve, at that time, we believe, pretty decent molecular saving. So for the pure hydrogen, we can achieve around 201 for the permeance, and the selectivity for against the CO2 for around 7, so which is pretty good. I mean, this is still arbitrary unit for most of the audience. So give you a pretty straightforward idea is, if we have a membrane around 10 centimeters in terms of length, we can purify up to 200 mils of hydrogen per minute. That's almost equivalent volume for a can holding in people's hands. So that's pretty efficient. So we were really excited about the results, and we talked to a lot of companies about the patent research office, whether someone will be interested in buying the technology for real applications. But again, if you still remember the repeated steps we need to perform before we get the coherent layer, this actually really block us entering the industrial area. For industry, people just want something that is easy, that is scalable, that is cheap. So how we can do that while achieving similar results? So we're starting looking at alternative technology instead of the titanium nanoparticles. So at that time, another thing came up to the community, that is polydopamine. Today, it's still pretty popular. It's pretty much like a super glue at the nanoscale. We can put a polydopamine onto anything, and it can bond with almost anything else. So that's pretty good material and pretty good chemistry behind that. So we immediately tried the same thing. We started with exactly the same type of substrate. We synthesize, we coat the polymer with a polydopamine. Then we try to grow it. We did exactly the same. The membrane looks very similar, but when we test the membrane, we found, okay, it's quite different. I mean, it's not that different. If you look at helium CO2 separation efficiency, they're quite comparable. So we have two types of membrane. One is the titanium nanoparticle, which we mentioned before. The other one is polydopamine, which we just introduced here. So if we try to compare those two membranes, even though they look very similar, the helium CO2 separation is pretty similar, but helium methane separation is quite different. This looks like for our newly made membrane, which is on polydopamine, the bulkier gas actually goes through the membrane quicker, which is extremely counterintuitive, because if you think about the process, typically you would expect the larger molecule to go through slower, but in this case, it's actually going quicker. That's really making us thinking whether we have done something wrong. But we have tested those results multiple times. We still get the similar results. So I thought, okay, there must be something different between those two membranes, even though they look very similar from the XRD, from the SEM, from the gas absorption results. So that's the beginning of another journey. I took the membrane to synchrotron. This is actually my first ever trip to synchrotron. Before that, I have no idea about what the synchrotron was, because I was a chemical engineer. So I studied the crystallization process of ZEEF on top of different substrate. And we can do some refinement, as well as we use terahertz spectroscopy to study the dynamic properties. I mean, after we'd done the refinement, we found, okay, for the ZEEF on ZFAD crystal, it's pretty much consistent. The crystal structure is reasonably consistent. But for the dopamine surface, it seems like the crystal is getting smaller. By how much? It's only by 0.3%, so that's not much, right? But once we put the model into a dynamic structure, looks like 0.3 change in the structure, in the lattice parameters, will actually significantly make the framework much more flexible. So that is something really bad for membrane, because for membrane, we want to have something rigid and tough, but seems like the polydopamine can make the material kind of more flexible. But that's actually making us thinking, okay, this is a pretty interesting phenomenon, because initially we thought MOF as a crystal, it should be like a metal mass, right? It's having defined pores, it will never change, it stays like that forever. But actually in the real world, the MOF structure is kind of dynamic. It's not super rigid. It's vibrating, it's flexible, and it's adaptable. So that's the first puzzle I had during my career, is how we can harness the flexibility and adaptability for the MOF. So that's kind of conclude my theme one research. So in today's presentation, I'll be talking all three different themes of my MOF related work. And then I will answer the first question I proposed at the beginning, which is the best material working with MOF. So let's pack the theme one first. Let's go to the theme two. I guarantee you at the end, they will come together very nicely. The theme two is called Janus membrane. That's another interesting theme about my research. Again, this is highly related to the CO2 capture project I did when I was a PhD. So after years spending in the pilot station, working on porous membranes, I thought, okay, so how we as a human being process the CO2. So from a chemical engineer's perspective, human body is very efficient for CO2 process. An average adult can process up to 5 times of the whole body volume of CO2. We're talking about 450 liters of CO2 on average per day. This is extremely efficient. So further look at what's the mechanism. Because we have this structure called alveoli inside of our loins, and the unique part for the structure is we have the bubble, which is kind of void bubble, allow gas to freely diffuse through the bubble. But also we have the blood flow and also the enzyme called carbonic anhydrase immobilized at the interface between the liquid and gas. The interesting thing for the interface is it will not only allow the gas diffusion, but also it will block the diffusion of liquid. This is pretty exciting. On the one side of the interface, it's hydrophobic. On the other side, it's hydrophilic. So that's making me thinking, okay, that looks like the enzyme has been put into where it can be maximized for its in terms of the efficiency. I ask myself, can we recreate a structure? Of course, as chemical engineer, we can create structures quite easily. I started with a hydrophobic membrane. Then we called a hydrophilic surface layer on top. That's very similar to the alveoli structure, and we can use the hydrophilic membrane in gas-liquid contactor with the enzyme being immobilized on the hydrophilic layer. So what happens is all the CO2 gas, once they enter the liquid phase, they will be immediately getting in contact with the enzyme, getting reacted, and also removed. So why this structure is so interesting is the mass transfer efficient for a molecule in the gas phase is much more higher compared with the coefficient in the liquid phase. So we're trying to solve the bottleneck for the whole system, and this one works really good. So if you compare the efficiency here, we are using somewhere about 2.97 milligram of immobilized enzyme, and we can achieve equivalent hydration efficiency for the CO2 when using around 13 milligram of suspended enzyme. So we call it putting all the enzyme into where it should work. After we published the first paper, I think, okay, we should give it a fancy name. Okay, so how we can call the membrane? I was kind of inspired by an Asian woman gold called Janus gold. Janus means Janus actually having different meanings. We have the meaning of interface, which perfectly fits the concept of membrane. All the membrane should be interface. And also the Janus gold have two faces. One face looking to the future, the other one looking to look back into the past. So in Oriental philosophy, we have Tai Chi, everything we believe having brighter side also have the darker side. So anything having opposing properties, we can call it Janus membrane. So I propose this picture. We have a mirror and the white panda will be black panda. Everything kind of reverse across the Janus interface. So we decided to call the membrane a Janus membrane, which is pretty nice paper, and we're happy this paper has been reasonably well cited. I will very quickly give you a few ideas how we can use the Janus membrane for. For example, anyone who have done wastewater treatment knows you need to get bubbles in the liquid to achieve the mass transfer, to achieve the oxygen dissolution to allow the bacteria to grow. But if we want to use a membrane for aeration, it's really hard because it has to be hydrophobic. Otherwise, water will go through the membrane. But hydrophobic is always aerophilic on the water. That means air bubble like to grow on the surface of the membrane before it's getting really big, so that can leave the membrane surface under the effect of buoyancy. Okay, so what happens if we use a Janus membrane? We can achieve fine bubbles. So this is what we did. We have polymeric membranes made from polypropylene, very cheap, commercially available. Then we coat the membrane one side with a hydrophilic coating. So we now have a Janus membrane. One side is hydrophilic, the other side is hydrophobic. We later perform quite systematic calculations on all the surface energy, etc. But long story short is once we use the Janus membrane, we can reduce the bubble size of the aeration by a significant amount of quantity. And that means smaller bubble means much higher mass transfer efficiency. So if you compare with the gas dissolution speed, our Janus membrane is much higher. in terms of the mass transfer efficiency in this case. That's one example. The other example, probably not really related to the MOF, but it's quite important topic for the membrane. Sometimes we have a process called membrane distillation. In membrane distillation, we want the membrane to be thick, so that because the membrane distillation is the driving force is the temperature difference across the membrane. So we want to have a thick membrane, so it can keep the membrane, can keep the temperature difference larger. But also we want to have a thinner membrane, so it reduces the mass transfer resistance, right? So that's pretty intuitive. But the real question is how I can make a membrane thick and thin at the same time. That may sound like something totally impossible, but in reality, we can achieve that by using Janus membrane. So we can coat the membrane one side with the Janus properties. We actually reduce the membrane pore distance without changing the membrane overall thickness. By using the Janus structure, we make the membrane efficiency almost doubled. So again, that's pretty exciting. I can talk about the Janus idea for the whole day, and we can use the Janus membrane for oil-water separation for one side, separating oil from water, the other side separating water from oil. I mean, we published zillions of papers on this topic, and also we expanded the concept of the Janus membrane into the energy area. So that's Janus membrane. We also try to say, okay, whether this is a good idea for the MOF. That's a theme 2. Okay, let's quickly go through theme 3 before we jump into the final answer to my question. Okay, theme 3 is also bioapplications. Bioapplications, I'm pretty sure it's getting really, really popular because people see the opportunity of using MOF, using advanced materials for bioapplications. We have been working on biomotors, nanomotors, and also the drug delivery sensoring, all the things people can be used as a MOF. But before we get into the details, I just want to give you some background information, how I come up with the idea. This again, come back from my chemical engineering treatment education background. I mean, I was looking at the wastewater treatment facilities process, and I found there's one problem. You probably heard, okay, so if you go to the supermarket, you see the baby milk bottles, you probably see, okay, it does not contain any BPA. BPA means bisphenol A. It's an endocrine disruptor. At that time, about 10 or 20 years ago, people started to realize, okay, those materials, those chemicals, which traditionally think it's not a big deal, but once they enter the natural water system, it's gonna stay there for a really long time because they are super nasty. They're very recalcitrant, which means very resistant to any degradation or decomposition. In the traditional wastewater treatment facilities, they have no capacity to deal with those kind of emerging chemical pollutants. And sometimes they even make those chemicals even more toxic. So how can we solve the problem at that time? I thought, okay, probably we can combine with the enzyme, which Mother Nature have been using the enzyme for material recycling and et cetera, et cetera. So as I mentioned, I'm looking at the component called bisphenol A, and we can put the enzyme into the bisphenol A solution, and immediately you can see it form kind of foggy kind of structure. That means we all like that because it's quite easy to remove from chemical engineer's perspective. Okay, but enzymes are all very expensive, they're very sensitive, so how we can make them practical? One thing is, by immobilizing the enzyme, we can make them much more robust. And we can combine immobilize the enzyme with filtration membranes that making the membrane bioreactive, but also making the membrane much more falling resistant. So it's kind of hitting 2 birds or even 3 birds with 1 stone. I'm pretty sure birds probably not like my metaphor, but that's the idea we're having. We can not only blend the enzyme immobilized nanoparticles, but also we can coat the enzyme immobilized nanoparticles on top of polymeric membrane. Okay, so that's probably not related to the MOF. But after working on the engineering aspect for a couple of years, one day I realized, I started thinking, wait a minute, if we have an enzyme, we have a bisphenol A, what really happened during the degradation process? You see, probably you can already tell, I really like asking questions, pretty to myself and to my colleagues, which make me kind of popular and unpopular at the same time. So let's get back to the topic. If we have an enzyme molecule, which I have shown here, this is the enzyme we use. What happens is when it gets in contact with the bisphenol A, it actually sees the electron from the bisphenol A, which we put here as a substrate. And the electron got transferred from internal pathways to an electron acceptor, which is oxygen in this case. It reduced oxygen to water. So I thought, okay, even though I'm not an expert in battery, but this looks like a battery to me. If we can get an electron out of the enzyme, it should be able to degrade the bisphenol A or any nasty material, but also generating electricity at the same time. So this may sound too good to be true, but we can actually make it happen. So what we did is we put the same type of enzyme on both cathode and anode, and put a proton exchange membrane across the different chambers. In the anode chamber, it only allows anodic reaction, and vice versa on the other side. So this may look a very simple configuration, but in the reality, we can make electricity while degrading the bisphenol A, which we mentioned before, which is very difficult and very challenging to degrade. So this is pretty exciting. I thought, okay, this enzyme works. How about other enzymes? The other enzyme we were looking at is called fomate dehydrogenase. Probably you're not really familiar with the enzyme. What this enzyme does is it can convert CO2 to formic acid. This may sound too good to be true, but after we put the same type of enzyme, both cathode and anode, and we bubble CO2 on one side of the chamber, it can actually generate electricity and also convert CO2 to formic acid at the same time. Of course, I have to admit the energy efficiency is not spectacularly high, but we can still achieve 0.1 voltage with a very simple configuration and setup. So you see, the biomaterial is pretty exciting, but so that brings us to the question, is the biomaterial a good candidate, a good player with the MOF? So how we can get the MOF to work with bio? I mean, I've been living in Australia for over 10 years. One of my favorite food in Australia, I believe everybody probably is lobster. But the painful bit for lobster is when you go buying a lobster, probably paying over half the price for the shells and also for the something you can't eat. Well, I really hate that, but it triggers me thinking, how does lobster grow shells on its own? I mean, of course, it's not only to make us poorer, but also protect itself. But how do those things happen chemically on the water in the bio world? The reality is, it's actually having a kind of bioactive layer called chitin, which can seize calcium, magnesium from water. So it can kind of like crystallize those calcium ions onto its surface to build armors around the soft, vulnerable tissue. So can we do that with MOF? The answer is yes, because all the bio things have so many different type of polymeric reactive chemicals like amine, carboxylate, and also hydroxylate group, etc., etc. The name goes on and on. So we can actually grow MOF on top of pretty much all type of bio entities. You can name it. We can grow on polymer, we can grow on protein, we can grow on living cell. The interesting thing is they actually provide additional support and protections for those kind of bio entities. They're making them much more rigid and robust, while still allowing the mass transfer, because remember, MOF is a porous material. Okay, so now I have pretty much finished the introduction of 3 different things. We still need to go back to the topic at the very beginning. At that time, I've been keep wondering what should I do as a scientist or as an engineer, because I find difficulty try to identify myself. You see, this is the photo I took a couple of years ago, back in 2019 before COVID, when the world was still one piece. We can still travel. I hiked to Norway and took this picture standing on the edge of the cliff, thinking about, okay, on one side that's technology, on the other side that's beautiful science. How can I find the magic stone? Try to bridge those kind of huge gap, at least for me, between those two huge areas. Actually, I'm gonna show you a few examples. I've been talking about MOF materials for such a long time, but MOF is not perfect. For example, this is the very first MOF I've been start looking at, zeolitic framework, image-isolate framework 8. It is a good material, zinc-based, low toxic, easy to fabricate in water, but it's not stable. How unstable it is, if we have a single crystal, we soak it in water or we expose it in the lab, like in Brisbane or Singapore weather, where humidity is really high, we actually see the decomposition from certain crystal lattice very quickly. This is the kind of, we're talking about overnight. So this is the one criticism MOF material get from chemical engineers is if we have such a poorly stable material, how would we be able to make a commercially available product out of them? We can't have something expire in 24 hours. So I was wondering how I can solve the problem. Okay, I'm not using a round slice because I was actually reading his novels since I was a teenager. He's, for those who don't know him, he's a very famous Chinese martial art writer. He pretty much make my teenager life very colorful. But unfortunately, he passed away a couple of years ago. So after his funeral, I went to his monument in Cambridge, where he was a student once, to pay a tribute to him. In front of the monument, I saw this book I read almost 20 years ago. Okay, again, it's a Chinese character, but if you don't know the character, I'll talk about the story I memorized is the invention of Tai Chi martial arts. Okay, so the concept of the Tai Chi martial arts is we use soft to conquer hard, and we use slow to beat the quickness. I thought, okay, this sounds pretty interesting. So what is soft and what is hard? From our concept, MOF as a material, as a framework, as a skeleton, it sounds hard. But what is soft? A biomaterial is soft, right? So what happens if we put those two materials together? I mean, we have done that for many other topics, but can we protect the MOF? Not only protect the bioentities from external attacks, but can we protect the MOF? So the first thing first is we do everything with a simulation and we do a calculation. Here we build up a very fundamental tetrahedron structure for the Z, centered by the zinc and connected by 4 imidazolate linkers. So what happens if we intentionally break one imidazolate linker and connect it with a biomolecule? In this case, a polypeptide. Okay, we're creating defects, but to our surprise, this defects is not really making a bad thing for the framework itself. It's actually making the remaining 3 bonds much more tougher. The energy of breaking bond actually increased by nearly 30 kilojoule per mole, which is a decent number. So this works in practice. How about in reality? So we compare 2 types of MOF. One is just pure MOF, which after synthesize, we put in the buffer, which is only pH 5. It's almost start decomposing immediately. But after we compose it with the polypeptide, it forms bonding with the MOF. As you can see, it's actually making the MOF much more robust. So that's provide additional chemical protections against the MOF. That's quite exciting. So polypeptide works. How about other materials? We tried the DNA, we tried polypeptide, we tried protein, we tried even living cell. They all work. So in this situation, we see the DNA is even better. You see the DNA, the composite DNA with MOF is we can still retain around 80% of the crystallinity after nearly over 2 hours, well compared with the pure MOF almost dissolved immediately. Because they have chemical bonding at the interface. So we're not only making the polymer, we're not making the bioentities much more robust, but the bioentity on the other side protect the MOF from chemical attacks. So we are using the Tai Chi martial arts concept. We use soft material to protect hard material. They kind of help each other. That's pretty exciting. Another thing, kind of inspired by bio, but not technically bio, is the Schrödinger's cut. It's still cut, so that we can still call it bio. The quantum material is always quite exciting, but it's quite difficult to make. But the MOF we have in super small pores actually giving us access to the quantum realm, that we can control the shape, we can control the size, we can control the chemistry. So if we can do the chemical reaction within the MOF, and hopefully we can still navigate the ocean of the tiny world using some very traditional, very classical inorganic chemistry. In this case, we can use P-box diagram to control to help us to synthesize metal oxide within the pores of the MOF. That's actually making the MOF much more chemically, much more catalytically reactive. So again, this is a very basic figure, not too much details. No, not really go to details, but you can see compared with the catalyst embedded on silicon oxide, which has been regarded as a very classical system. The ruthenium oxide embedded in the MOF 808 is much more efficient. So I'm pretty much getting to the end of the talk, but we still haven't really answered the question: what is the most compatible matrix with MOF? If you can recall my talk, I've been talking about inorganic materials. I've been talking about polymer materials. I've been talking about genus structures. We've been talking about the biostructures. But it seems like we still haven't got the answer to this question, right? But one day I realized, okay, probably the question itself is the answer to itself. So the ultimate answer to the compatibility for the MOF is MOF. If we can use MOF to composite with another MOF, or use MOF as a continuous layer, as a matrix to bond with another type of MOF, we will never have any incompatible materials, incompatible issues, because any MOF should be compatible with itself, right? But the real question is how. When I first joined the Cambridge University, I worked with Tom Bennett, Professor Tom Bennett. At the time, his group has been very famous for discovering the melting and the glassification, vitrification of the MOF materials. So all of the huge family of the MOF, Tom found around 4 or 5 at that time can be melted into liquid. Then after quenching, we can have glass. So to me, as a chemical engineer, this actually is extremely useful and exciting opportunities, because we can use the MOF glass and MOF liquid for a variety of different compositions and composites. So sometimes we refer our chemical engineers as cook. So you can see we can actually cook the materials for different purpose. If you look very carefully, this picture here, blended zip glasses, which I make the picture, is a croissant. I change the color of the croissant theme and make the zip blended glasses. So we can actually cook a lot of different structures, properties, and composite using the MOF glass itself. So I give you a few different examples, and I can show you how exciting those areas are. One very stereotype crystal glass composite is whether we can compose the MOF with MOF. We choose different type of MOF. One is glass forming MOF, which can be melted. The other one is not really glass forming, so it stays crystal. What happens is we melt those two materials together, we get a composite glass, which contains glassy phase, which is amorphous, and also crystal phase, which is crystalline. Traditionally, those kind of two materials are not really compatible, because crystal and amorphous, they're pretty much the end of the spectrum for the material area. But we managed to make the composite by combining those two traditionally not really compatible materials in this new form. As you can expect it is a glass, so we can make thin film, we can cast things, we can make palette of the material. And something really, really exciting, and also why we choose the MU53 as a crystal base, is MU53 is quite unique. It has a wine rack structures, which is my favorite furniture in the house. It can hold multiple wines, but the wine rack structure is not really, I would say, obedient. The synthesized ML53 contains the ligand, contains the solvent, so it stays large pore phase, but it's filled with all type of things. We have to activate the MO53 with high temperature, becoming large pore phase, but this phase is not stable. So cooling back to the room temperature will lead to a small pore phase. That's not a good thing for us. But how we can do that? I mean, by compositing the crystal MO53 with glass, we can use the high temperature MOF glass as a super glue to freeze the large pore phase of the MO53. I mean, it's a long, very long sentence. But long story short is we can freeze the large pore phase within the glass, that making the composite glass much more porous compared with either of the parental phases, because one of the parental phases will become a kind of small pore phase in this case. So that's very, very interesting, very exciting discovery for us. So the other thing is we only, as I mentioned at that time, we can only have access to a few number of MOF can be melted. So how we can functionalize the MOF, how we can understand the melting mechanism of the MOF is simply by functionalize the MOF structure itself. I mean, thanks to the chemistry of coordination chemistry, we can use different functionalized ligand to functionalize the MOF glass as the crystal material does. So by putting one atoms onto the benzoimidazole ligand, we managed to make the halogenated MOF liquid and halogenated MOF glass. You may think, okay, only one atom, that doesn't look too much different, but we were kind of surprised to see how much difference it can make in terms of melting temperature. Even though it's only one tiny difference, but the melting temperature difference spans over 50 Kelvin for different materials. That's quite a lot. So some of the melting temperatures very comfortably give us access to study their melting mechanism by using synchrotron terahertz spectroscopy. And we can track the peak positions against the different temperatures. And this peak position, after fitting with the Bose-Einstein distribution, it fits the distribution very nicely. With different forms, it follows different slopes and follows different coefficient. So that can be, again, the coefficient can be very well agreement with the melting temperature of the framework. So we can very comfortably say, okay, the melting mechanism is really the stretching and the deformation vibration for a few ligand and the coordination bound within the framework. So now we pretty much have two sides of the equation, right? We have the material that can be used to make a composite as a filler, and also we have a different type of functionalized MOF glass as a substrate. Now we can go back to the original topic. What can we use it for? Again, I've been working on a variety of different topics, so I will quickly show you what it does, what it can offer. One thing for MOF glass, as a membrane person, the first thing I tried is to make membranes. Typically, initially I talk about all the composite membranes. Once we have the defects in the composite material, it may stay there forever for traditional materials. But in our case, we can melt the MOF glass inside the polymer, make the membrane, I wouldn't say defect-free, but reduce the voids by a significant amount. So the top one is the composite membrane before melting. You see all the red bits represent the voids at the interface. But after melting, it's becoming much, much less. We have done the quantitative analysis, it reduced by 98%. So that's actually delivering a membrane much more selective. So we were really excited to call this process toasting MOF mallows. It's like toasting marshmallows when you are camping. So the other thing is whether we can use MOF glass as a substrate for membrane makings. We can make mixed matrix. Can we make mixed matrix membranes using MOF glass as a polymer to replacing the polymer? The answer is yes. Of course, we can almost choose endless options to make the triple-M membranes using MOF glass. In this case, we demonstrated using the zeolite traditional zeolite powder-etched material, difficult to make membrane composite with a zip glass. Because their interfacial compatibility is so good, we're actually not creating any additional defects in here. And surprisingly, you can see by increasing the load of the zeolite, we increase the permeance of the C4H6 and also increasing the selectivity for different chemicals. So this is something we don't see very often in terms of the mixed matrix membranes, because typically you will lose kind of compromise between the permeance and the selectivity within the composite material. And also a composite MOF structures give you very fine-tuning structure at the interface. So this is not only interface between polymer and MOF, but also you can engineer the interface between different type of MOF when you're putting two layers together. So what can we use it for? So this is mimicking the natural ionic channels across the cellular membranes. Again, this is the kind of Janus structure because in natural cellular membranes, you have the Janus structure to allow highly selective ion separation. So we can make MOF membranes and then make the membrane highly selective against different ions like lithium, potassium, and sodium. Probably not go into the details given the time constraints, but that's a membrane application. We can also use the MOF glass for other things. Like one of the things is optical. Anyone in this research field probably heard about the perovskite. It's becoming kind of buzzword. Each issue of the Science or Nature paper, there should be a perovskite paper. It is really exciting material, but it's not stable. When I'm looking at the stereotype perovskite, the cesium iodide, which people using for solar panel, I immediately see the problem for the material. I draw a phase diagram for this material. It's not stable against almost anything. It's not stable against water, vapor, or even light or oxygen. But the big thing is that it's not really stable against water. So against the temperature, the real thing is at room temperature is non-perovskite, what we call yellow phase. So we have to heat it up about 325 degrees to allow the crystal phase transition to becoming a perovskite phase. But during the cooling, it will spontaneously get back to the yellow phase, which is kind of useless at a temperature 250 degrees. So I thought how we can solve the problem. So the first thing came into my mind is whether we can design a MOF glass that can freeze the crystal phase above 250 degrees before it goes back to the non-perovskite unusable phase. We can freeze it at high temperature phase, about 30 degrees each. Again, freezing at 300 degrees is not really sensible, but that's what actually we did. We designed the MOF glass and which having the phase transition temperature above this temperature, and we can put them together with the perovskite, and that actually allow us to freeze the perovskite phase at around 325 degrees. And we have done substantial calculation to understand the properties at the interface, properties at the phase transition, etc., and we end up having something very efficient. So pure perovskite is pretty good, but our composite only contains 25% of perovskite by weight. We can see the brightness is somewhere between 2 to 3 orders of magnitude higher. So this is not 20 to 30%, but it's 100 to 1,000 times more efficient compared with pure perovskite. This is very, very exciting. And we can mix and blend different materials, make white light LEDs. And again, it's quite robust. And also we can synthesize, we can process them into different shapes. Super exciting. And also because it's the chemical information, the structural information, the property information across the composite is so rich that we can't help studying the properties of the composite. We want to understand what's the best composition, what's the best sintering temperature within the composite. So we identify, okay, if we put 5% sintering at 225, 300 degrees each, seems like we can get the maximum brightness. And we are very lucky to work with a team of very advanced TEM experts. They actually use cathodoluminescence, which is they can look at the light emission of the nanomaterial under the TEM. And by fitting the peak, we can immediately see, looks, so this region, that's all the perovskite phase. That's where it's becoming really bright. If you look at the peak width, actually the peak width at the interface is getting somewhat broader. So this kind of indication, the interfacial properties must be different from the bulk. And again, as I mentioned, because the information for the composite is so rich, we can actually retrieve those informations by using advanced technologies. So in this case, we use the ELS, energy loss spectroscopy, on the TEM to study the structure at the interface, which can be later fitted with the powder diffraction power distribution function using single-shot X-ray. So what we discovered is the perovskite phase is not really a bulk. It actually can dissolve within the MOF liquid and MOF glass. This dissolution process can make the material healing the defects at the interface. That's why we are seeing a huge increase in terms of the efficiency for the perovskite. So that's really, really interesting. And also on this topic, we published 2 perspective papers. So any of the audience who are interested in can have a read. And another thing is, because they are glass, they are super processable. We can make coatings, but different variety of different options by using mechanical chemistry, by using deposition, by using even deep coating, spin coating, whatever you can name it. So this is the coating pictures we made. We can coat on different type of substrate, and also after coating, because after coating we can simply do a thermal treatment. It can spontaneously melt it on the surface of the substrate, right? So that we just demonstrate this can be used for, say, like electrode, right? In this case, we put a cobalt-based glass together with ions, and we just coated on the top of carbon cloth, which is quite inert, quite difficult to coat. But in this case, we use ball milling to coat the MOF glass onto the carbon cloth. Then we melt the MOF glass to get an electrocatalytic reactive electrode. So that's a long name. We also try to benchmark our performance with the well-studied platinum material. Platinum electrode is quite comparable, but particularly appealing considering we're using relatively cheap material and our electrode size is much, much larger. So I think that's quite a long talk. So hopefully you're still engaged, and hopefully you still find my talk interesting. So if you're interested on this topic, we have published a review paper on this topic called Metal Organic Framework Glass Composite in Chemical Society Review. So if you're interested, you're welcome to have a read and send me any thoughts and feedbacks. I'll be very welcome to that. So to wrap up, I think I wouldn't call teaching old dogs new tricks, because MOF is still pretty young. But if you think about the whole materials domain, amorphous material is probably a very old area. So by using the amorphous MOF and liquid glassy MOF, we can combine MOF materials through interfacial engineering, and we can design different properties. Once we have different properties, we have different applications. That's happy day for us, right? So at last, what I found is probably the interfacial engineering is the ultimate force for chemical engineers, material scientists, and also chemistry researchers. So I would want to say, may the ultimate force be with you. Of course, that's a lot of work. I couldn't do that all by myself. I got a group of fantastic mentors and collaborators. Special acknowledgement to Zhao, who has been recently selected as a fellow of Australian Academy of Science, and also Professor Vicky Chen, Tony Cheatham, Tom Bennett, as well as so many collaborators I've been privileged to work with. I can't got enough time to read the name for all of them. My group members, also a big call for them, and also a founding body who paid my research. And last, I put my name and also my contact emails, jingwei.ho@uq.edu.au. We are a relatively young research group, so we are very, very keen and very open for collaborations. I'll be very looking forward to any questions and discussions, either through the online chat or through email down below. Thank you.
Thank you very much, Jingwei, for the wonderful presentation. So now it's time for the Q&A. We have 2 online questions, and let's try to answer those questions first. The first one is from BPN. Can we use the Janus membrane as a flexible electrode material for energy applications?
I think the short answer is yes, definitely. I think there's quite a few examples we try to mention in our paper. So one example is for the OER reaction. OER reaction, you want to have the gas diffusing into the liquid phase, and you want to have the catalyst staying right at the interface. So which is very similar to the carbonic anhydrase case I just mentioned. So I think that's a perfect example of using Janus membrane, can be very useful for energy application. The other example I showed here is called osmosis energy harvesting. Professor Lei Jiang from Chinese Academy of Science, he is a very well-established expert in this area. So the Janus membrane putting inside of the saline water can allow the ion directional diffusion from one side of the chamber to the other. So the ion diffusion can create energy using the Janus membrane. So yes, I would say Janus membrane for energy applications is still at the infant stage, and we definitely can do a lot of things on that.
Thank you. Next question from Laurie. In the case of a melted MOF, how can we check that the material is intact in the liquid phase?
That's a pretty good question. I mean, depending on what you are trying to melt the MOF with, it is because if you look at the temperature of the MOF melting itself, typically we're talking about 300 degree, 400 degree-ish. So that means it is quite thermally challenging, but that's not the whole story, because once the MOF is melted, it's behaving something similar to an ionic liquid. It's highly reactive. So a lot of materials will not survive against the high temperature treatment or co-melting with MOF. So that's maybe the bad news. But the good news is the MOF liquid is highly viscous. That means even though thermodynamically it's not stable, but kinetically we can still like quick melting and quick quenching. We can still preserve the encapsulant. So if you want to say how we can monitor the degradation, a few techniques. If you're trying to put a crystal into the MOF glass, we can use in situ XRD to study the structure, which is very well understood. The other typical method which we use very often is DSC TGA combined with MS, because if anything decompose, there must be something out of the flue gas, out of the TGA MS. We can keep on track.
Thank you. Another question, or I would say suggestion from Wenlong. Is it possible to combine the meltable MOF with a highly porous COF and then melting or sintering to form a highly porous MOF COF glass membrane?
That's exactly what we're doing right now. but the challenging is usually COF is like highly porous. The pore size is pretty large. You got the interpenetration issue for the COF itself, and also the thermal stability, thermal compatibility issue. But now we can reduce the melting temperature for MOF to around 200 degrees C, which is pretty low from our standpoint. But for the COF people, it's still very nastily high. We're still trying to find somewhere we can meet in between.
Okay, thank you very much. I actually also have some questions, and of course, the online Q&A is still open for the audience to ask questions. But before I start to ask my questions, I want to highlight that we have the YouTube channel for all the past MOF 2024 webinar recordings. So if you are interested in any of the past webinar, please go to our YouTube channel, and you can find that from the chat box. Okay, so my first question is, I'm quite interested in one of the study where you show that a polydopamine layer will make the ZIF8 more flexible, is it?
Yeah.
What is the reason why the ZIF8 becomes more flexible? Because if I look at the unit cell, it becomes smaller after interacting with the polydopamine, is it?
Yeah, I think you are exactly right. So it's actually getting smaller. So the unit cell size is not that different. It's only about 0.3%, as I mentioned. But actually, I think two reasons. One thing is it's actually creating some defects for the crystal itself, so that making it much more mechanically less stable. The other thing is this is based on the DFT calculations. We put two unit cells into the DFT model. One is larger, the other one is smaller. So the smaller crystal module can reduce the rotation energy for the imidazole ligand. But I think that's another reason for the increased flexibility for the smaller crystal. I think probably the main reason is it's not at the lowest energy phase. That means we are actually disrupting the framework structure, making it more less stable, or in other words, more flexible.
Okay. Yeah, because this is very important. This will generate more flexibility to the pores. In some cases, maybe you'll find other applications.
Yeah, that's right.
And you mentioned that the Janus membrane, and I understand for the Janus membrane, you need to have both the hydrophilic and hydrophobic part together, right?
Yes.
But how do you solve the compatibility issue of this hydrophilic and hydrophobic part? How do you make sure they stick together firmly?
Again, I think that's also a very good question. We have to get around the problem. So you can see some technique we use for Janus membrane is one of them is polydopamine. Polydopamine is pretty easy to control. We can control the deposition depth thickness. In this case, you can see you are the expert in the membrane. So we have the membrane. We are not we are making one side treatment, but this is not increasing the thickness of the membrane. We're actually coating through the pores.
Yeah.
Coating into the pores. So because polydopamine is pretty easy to control, quite stable. So that's not really having too much incompatibility issues. The other example I showed you is by using, that's very old work, by the way, by using carbon nanotubes. And the carbon nanotube through filtration coating, I think not only we are seeing some coming of one of our force bonding, but also probably some of the fibers getting penetrated into the polymer membrane pores. That's actually making it quite robust.
Yeah, very, very interesting. Maybe
but
you can, maybe you can try some surfactant molecules, those with both hydrophilic and hydrophobic part.
That's a good idea. Yes.
Yeah, and I am very interested in your observation, where for your ZIF8 you replace one of the zinc nitrogen bond with zinc oxygen bond, and you observed dramatically improved stability of the whole framework.
Yes.
And this is fantastic. I mean, and that work remind me of COF20. You're familiar with COF20? This is this is a MOF report by George Misu's lab, and this material has an extremely high stability towards not only water but even steam, so that the BASF and the Svante scale it up to, I believe, close to ton scale for carbon capture, where you use a temperature swing to regenerate the material. And the structure of the COF20, the inorganic part is a zinc, 4 coordinate zinc to 2 oxygen and 2 nitrogen.
Yeah.
So it's probably because of the mixed coordination of both nitrogen and oxygen that make the material extremely stable.
Extremes. Yes. Yes.
Yeah, but I'm very glad to see that you have found this. But if we can know, in terms of chemistry, why this kind of arrangement will strengthen the framework stability, that can help us to overcome the stability issue of the MOFs without referring to some expensive metals such as zirconium or hafnium.
Yes, that's right.
Right?
Zinc,
Because zinc is
I
very
would
cheap.
still say, yeah, zinc is so easy to make. So
Yes.
I'm still primarily working with zinc-based MOF.
Yes. My last question, since we don't have any question from the audience, my last question, I'm very curious and also quite interested in your meltable MOF. And I am wondering, what are the forces that can trigger the melting process?
Okay.
And
So
what are the conditions
that's
you can use?
I mean, that's a very good question. So let me see what I can find the slides. So I think my former supervisor and also the collaborator, Tom Bennett, he has actually done quite a lot of study on the melting mechanism for the MOF. I would say it's somewhat similar to melting of other materials. You have to provide enough energy into the system. In this case, it's a framework to allow the transition, breakage, and recoordination of the bonding within the framework. But this has to happen very quick. Otherwise, you probably will lose the ligand by thermal decomposition. So that's basically the fundamental mechanism of the melting. But everything follows the physical chemistry process. So you can use the entropy to reduce the melting mechanism, melting temperature. Increase the entropy will reduce the phase transition temperature because of Gibbs equation. So that can be done either by increasing the complexity of the system, introducing the composite, or increasing the let's say the host gas composite structure for the MOF. So I think Tom have done some study by introducing the imidazole-based organic the iron liquid into the framework, so that can significantly making some previously unmeltable MOF meltable.
I see. I see.
So still an energy field to play.
Yeah, I think this is a very interesting group of materials. It can hopefully preserve some microporosity, but at the same time, it can be easily processed like a liquid.
That's right.
Yeah, from the membrane point of view, this is a dreamy material we are looking at.
Yeah, we're thinking about hopefully this will be the either next PEM or the next thermally arranged MOF. Hopefully we can call it TR MOF.
Yes, yes. Thank you.
Yes.
All right. Since we don't have any Q&A, so we will end the webinar for today's webinar. So again, Jingwei, thank you very much for your time.
It's my pleasure. Thank you so much.
Thank you.